It's like 3140.
30 out of 90. Good afternoon, folks. The dedicated 30 people out of 90 that are here. So, started in last time on lab 3, and I want to talk some more about lab 3 because there's a couple of big pieces. One is analog digital conversion and direct memory access. But first, I want to ask, are there any questions on lab 2? I saw some strange code yesterday for lab 2, and I want to talk about that a little bit. Before that, though, a student asked the question of what was the demo time for the final project. Now that's thinking ahead. And the official due date for to demo the project is your last regularly scheduled lab period. That would be the week you get back from Thanksgiving break. I'm going to make an optional, no penalty extension into the next week. I think it's study week. First couple of days of the week. And so the due date is the last week of classes. If you want to get extra points for being early, you have to be early with respect to your normally scheduled lab period. But you can demo with no penalty up through the extension period, and I don't know the dates yet. I'll have to look at it, but it'll probably be Monday, Tuesday, Wednesday of the week following the last day of classes. And what I'll do is to schedule half-hour time slots from 9 a.m. until 4 p.m. and you will have to sign up for a slot at some fixed time in the future around the 1st of December or so, or maybe the before Thanksgiving break. And the requests for time slots will be handled in the order that I get them in the mail. After 1200 on the day of that I specify. So you can't now email me and say I want a demo at the last possible moment. That'll happen sometime in the future. I'll put out instructions on how to do that. But there will be a little extra time after Thanksgiving break before you have to demo. When you demo, you must also have a good first draft of the web page that you're going to hand in. The web page is part of the demo. The documentation is part of the demo. That sounds like a great thing to do over Thanksgiving break. Documentation. Yeah. Any questions on that? That's way in the future. That's just to sort of warm up your brains with regard to that. Any questions on that? Any questions on lab 2? Oh yes. So what I saw one group doing was to assert the chip select line, write the SPI, write SPI again, wait, and deassert the chip select line. What's wrong with that? So assert chip select, write SPI, wait, and deassert chip select. What's wrong with that?
You should do a
If you ever do a read, if you ever expect to get the write data back from a read, you must do a read for each write. That is correct. If you never do a read, which is the case for a DAC, you don't actually have to do a read because you're just blowing away the FIFO and it doesn't matter. But there's a more basic problem. Who else had a hand up? Somebody else had a hand up over here. Yes?
If each write is 16 bits, you have to reassert between them.
That is correct. That is one mistake. You have to reassert, you have to deassert and assert between the writes. And there's another problem, and that is that writes are not blocking. They throw 16 bits into the bucket and they return instantaneously. That means if you do 2 writes in a row, you're overwriting a buffer. So not only do you have to deassert, you have to in fact wait, deassert, and then assert deassert the chip select, reassert the chip select, and then write the second one. The results you get by 2 fast writes in a row are really hard to understand. But what I think happens is that the buffer is filled by the write. The buffer on the DAC now, the DAC buffer is filled by the first write. It's a 16-bit write. It's filled by the first byte. There's no deassert. You send the next 16 bits. It writes over the first 16 bits. And then when you deassert here, you see only the second signal and not the first signal. And so the effect will be that one of the channels appears to be dead. Any other questions on Lab 2? Oh, I saw another interesting one. The little plugs that you put the phone jack into, they have 3 terminals on the bottom. The one near the plug is ground, and one of these is left and the other is right. And I can never figure out which it is, but it doesn't matter because you could always move the speakers like that if you care. And I saw somebody that had these wired together. What happens then depends on the impedance characteristics of the left and right channel outputs. It might just destroy both channels of the DAC because you're hooking 2 voltage sources together. Remember that the DAC is you're going to have the DAC A hooked here and DAC B hooked here. If the DACs outputs are both very low impedance, it'll just destroy the output stage of one channel or the other or both. If they are fairly low impedance but high enough that neither of them is destroyed, what will happen? So these are the Thevenin equivalent resistances of the left and right channel, and then we have the Thevenin resistance of the amplifier input, and we have a left channel voltage and a right channel voltage. What will happen? Well, let's say these are a few, maybe let's say this is 100 ohms, something like that. What will be the effect? I saw your finger go like that, but I'm not quite sure what that means.
It's going to flow through.
Well, right, you'll get current flowing this way or this way for sure. And what will be the effect? By superposition, what will be the effect? By superposition, we could hold this at 0 and we have a voltage 1 to 2 voltage divider for the left channel, or by superposition we can hold this at 0 and we have a 2 to 1 voltage divider for the right channel. Therefore, what will appear here is the superposition of the two channels. In other words, it'll add them. It'll add them together, divide by 2 and add them, and it'll take the average of the two. So what you'll hear is both signals coming out of both channels. Slightly odd, but okay. Anything else on lab 2? Is it going okay? Keypad working? Hands? Mostly. DAC working? DDS? Yeah, both? Both, yeah? No? Yeah? That's... What does that mean? Yeah, I mean, yeah, it's kind of methodical looking. Method. Okay. So... I suspect that means you would like lab time on Monday morning. Yes? 9 o'clock or 10 o'clock? 10? Did I hear a 9? We're going for 8? 9, okay. 6. I'm usually here by 7, but I'm hardly ever here by 6. If I get here by 6, I have to get up at 3:30. That's a little early. So, okay, 9 o'clock it is, Monday morning. I will check with 2300 to see if they have a lab next week. If they don't, I will keep it open Monday afternoon also, but I have to check with 2300 first. Whatever announcement there is will be on Piazza. So, but you can count on Monday morning. Do you want Tuesday morning also? Yes? Possibly? Let's think about that on Monday. Okay, moving on to lab 3. The last time I talked about the game in general and the ball dynamics in some sort of vector notation. We're going to calculate the difference between the position of two balls and calculate the difference of the velocity, because that's the only thing that matters, is the relative speed and the relative position. And then form this homely looking structure. And again, what we're doing here, boink, is kind of a highly encoded version of projecting the velocity vector, the net velocity vector between the two, onto the collision direction. So if this is Rij and this is Vij, what we're doing with the dot product, of course, is to find the scalar component of the velocity in the r direction. And we know that's the only velocity that can change because there are no forces that are tangential, so only the velocity in the direction of impact can actually change. Do you recognize this particular bizarre looking thing as in terms of trigonometry? Do you recognize it? Can you say, oh well, Rij over the magnitude of Rij is just, so let's say that this is Rij. This is just the angle theta with the x-axis, cosine theta in the x-hat direction, plus sine theta in the y-hat direction. So really, this is a fancy way of writing a vector version of sine and cosine. Right? You can draw it all out and you can show it's the opposite over the hypotenuse and the adjacent over the hypotenuse, and it all makes sense. But what I'm doing here is, first of all, another way of saying it is, we're taking r and we're normalizing it so that it becomes a unit vector in the Rij direction, and then getting the projection of Vij onto the unit vector. And then we're using the sine-cosine relationship of Rij to turn that back into xy coordinates again. So we're finding the chunk of the velocity in the direction of the collision, and then we're turning that back into velocity components in x and y direction with this, by taking the sine and cosine of it. So, are there any questions about that? That's probably pretty far. It needs to be dusted off someplace back in the part of your brain that did Physics 1. And that's 3 years ago for you and 49 years ago for me. But I go through this every year, so it's not quite as dusty in my brain at this point. And then we've got to integrate it to form speed. But I thought it might be a good idea to write out a little bit of pseudocode here, because one of the things I'm asking you to do is under a varying computational load. When the game starts up, there's going to be no balls on the screen. There'll be no balls on the screen. You got the empty field, the quivering paddle sitting there, the catcher. The first ball flies on, goes in some direction. The second ball flies on, goes in a different direction, bounces off. Third ball comes on. Every ball that you add takes more computation. I'm going to ask you to keep a constant frame rate in the while changing the amount of computation per loop. And remember that this is not a preemptive threader. When you say wait 15 milliseconds, when you do a PT wait time 15 milliseconds, what you're saying is wait at least 15 milliseconds. Stall the process for 15 milliseconds. What I want you to do here is that every time through the thread should be exactly 67 milliseconds, 1 over 15 frames per second. So I thought that that was obscure enough that I might write that out. How do you make a constant time thread if you can't do absolute, if you don't have a preemptive system? And what you can do, so I call this compute balls, and what you can do is, first of all, get the thread at the beginning, get the time at the beginning of the while loop, do a PT get time, returns the time in milliseconds, then do this possibly n squared calculation for the collision of all of the balls that we talked about last time. So that's just I just copied this code into the pseudocode into this routine. And then for each ball, we're going to need to erase it update the ball velocity using drag and possible wall collisions, update the position of the ball, and then redraw it. Unless, of course, it goes off screen or you miss it, and then you're going to have to recycle it. You're going to have to disappear it from the screen and put it back someplace to be restarted from the right-hand side of the screen. So if a ball goes off this side of the screen and just disappears, it's going to end up being held over here for a while until it goes back on the screen again. So we might have to recycle ball I, or we have to redraw it. Then inject new balls into the playing field, if any. Check for user interaction by reading the analog to digital converter and possible buttons. But the analog to digital converter is going to be how you record the position of the potentiometer that you use to move the catcher up and down. So you have to read the analog digital converter in a timely fashion. And 15 times a second actually seems like a minimum. I think some of you will probably notice lag at that speed. You might actually want to read it faster. I forgot to put in here, then you have to redraw the paddle. You have to race and redraw the catcher here because that's going to be moving. And then down at the last line in the while loop will be to do a PT get time again, subtract the beginning time, and then subtract that whole thing from 67 milliseconds. So you're going to wait a time. You're going to wait the residual time that it takes to get to 67 milliseconds. The get time versus begin time will tell you how long it took to do all the rest of the calculations, and then you're going to wait a little while longer to get to 67 milliseconds.
What will happen in our code if that number becomes negative?
Oh, that's not good.
Yeah.
If the wait time becomes negative, what will it probably do if that's an int? What would you guess that it would do? Could explode. I might have done an error trap on that to make sure it doesn't happen, but I didn't, I don't think. You could rewrite PT yield time macro to do the check, but if there is no check, what will happen? A negative number treated as an unsigned looks like a very large number. And so this will go dead for about 5 weeks. So you'll get a thread execution time which is unsuitable for animation. So what you're going to do is start out with a low number of balls, say 5, get this thing running, maybe read this value out so you can see how long it takes, and then scale up from there. Yes?
Is this the only thread?
Is it the only thread? It could be the only thread.
With the sound, but that's not.
The sound is not going to be a thread, though. It'll be well, yes, all right. So you could, I forgot to put that in here, too. Inject new balls, check for user, check for, if there was an increase in score, if there's an increase in score, you have to, or a decrease in score, you have to play the sound, which means that you have to start but not wait for the end of a DMA burst. Starting a DMA burst is very quick, but you may have to do that. Or you could throw a flag which causes another thread to quickly execute and start the sound. Set a semaphore that causes another thread to execute and starts the sound. The other thread cannot play the sound, nor can, for efficiency, neither can you have a interrupt service routine play the sound. Rather, the DMA controller is going to have to play the sound. And I'm going to talk more about that. Sounds are probably going to be fairly simple. Maybe something like a decaying sine wave with a time constant of decay of, I don't know, 70 milliseconds or so. That'll make a bing kind of sound. Things that have a fast onset, sine waves, which start with a rapid onset and decay exponentially, sound a lot like a struck glass, or a drum, or some sort of impact. So that's not a bad kind of sound for this. What else? So I need to add something about sound production and updating the catcher. Okay, I'll put that in. So what do you want to hear about next? DMA or analog to digital conversion? DMA. Good choice. So direct memory access has its own page here. And you are probably going to want to look at the reference manual, chapter 3. But it's daunting. Actually, there's two chapters that are interesting. One is the structure. Chapter 3 is the structure of memory and how memory is accessed. And then chapter 31 is how the direct memory access uses memory. But the short answer is can be shown in one diagram here, which I'll try and shrink onto the page. There's up at the top is something called a priority interrupt controller. Let's ignore that for right now. There's PIC32 CPU, and side by side with this is a completely separate processor. So this is like a coprocessor on the chip, heterogeneous coprocessor. The PIC32 has an instruction issue capability. It can put an address onto the bus matrix that requests an instruction. It can simultaneously put an address onto the bus matrix which requests data. Simultaneously with those two, the completely separate DMA controller can put a address request, a read-write address request, onto the system bus. So there are 3 input ports to this bus. At least, there's actually more than that. The CPU we're using has at least 5. And there are 3 targets. Instructions have to come from flash. They can come from data RAM also. Never mind. They can come from data RAM also, but you have to work at it. Data addresses include flash, data RAM, and peripherals. DMA can hit all 3 of these. So you can, but a given address source, a given target, can only take an address from one source at a time. So if the PIC is asking for something from flash memory, the DMA controller cannot also ask for something from flash memory on the same cycle. It'll be queued up for one cycle. There are actually, on our chip, 4 channel controllers within the DMA unit. So you can control 4 separate data streams from 4 separate controllers, which are then priority multiplexed onto the actual address bus. So only one at a time actually happens, but logically speaking, you can keep 4 different data streams running at the same time. Tamid and I wrote a program that used one DMA controller to run a television, which requires constant update, unlike TFT screen. One channel to run the television, one channel to read the A to D converter, and another channel to feed the DAC, all using with separate DMA channels, all happening logically at the same time, but in fact on the bus they're interleaved. So the key thing here is that this is separate hardware. It runs at the same time as the CPU. It does not steal cycles unless you're unlucky. So the CPU is running at full speed. The DMA is using data capability on the bus which is left over that the CPU is not using. And therefore you get a net speed up for I/O. In the case of audio, where you have to put out a few thousand samples a second, this can be quite a considerable speed up. Because even though writing a register is fairly quick, if you put that register right into an interrupt service routine, it takes at least a couple of microseconds to execute. So this is going to be an alternative to using interrupt service routines for moving data. And you say, well, how does this possibly work? How could you time this? How would it? And the interesting thing here is that the interrupt controller can generate flags for any hardware event for which there is an interrupt flag. All of the timers, the ADC, UART, every device can generate an interrupt. Anything that can generate an interrupt can set a flag which will start a DMA transaction. So that the hardware can trigger hardware with no interaction from the CPU. You can actually go further than that. I wrote I'll show you an example in a day or two, that where the ADC, the analog digital converter, is triggered by timer 3. So the ADC is triggered from timer 3. So this triggers the ADC. The ADC done flag, which could trigger an interrupt service routine, but I'm not using it that way. The ADC done flag does not trigger an interrupt service routine, but rather a DMA burst to move the ADC value to memory. So the timer 3 flag is directly triggering the ADC. The ADC flag is directly triggering the DMA burst to memory. So data makes it from the ADC to memory at a regular interval as determined from the timer with no CPU cycles used. That's very cool, because you have but it also means that with n peripherals, you have the possibility of n squared possible communication paths between them. So that the peripherals become a toolkit for building structures that are outside the CPU but still do interesting stuff. For lab 3, we're going to use a DMA in a fairly simple mode. But first we have to build up a little bit of vocabulary. The terminology, yes. So an event is any system that can initiate or abort a DMA transfer. I mentioned that. A transaction is a single word transfer up to 4 bytes. And they're in some sense atomic. They happen in a burst, a tight burst. And but what is controlled by an event being, say, a flag being set, would be called a cell transfer, which can be one or more transactions per event. So you can transfer as little as 1 byte or as much as all of memory on one event. The cell transfers are structured into a block transfer, which will be one or more cell transfers that start with some trigger. For instance, the human or the program might set up a block transfer and then step back and a gigabyte gets moved before you do anything again. And the channel remains enabled until the entire block has transferred, unless you do something to stop it. So then, what we're going to do for this lab is you're going to use a thread to set up a block transfer, and then a timer ticking will start each cell transfer for you with no interrupt. So you're going to use a thread to start a block transfer. And then each cell transfer making up that block transfer will be triggered by a timeout, by a timer match. This is a hardware connection. So there's no software involved in this timer match cell transfer. Therefore, you get good CPU efficiency for the cost of setting up the block transfer once per sound. So you're going to go bing. There might be 2,000 samples on here. So let's say that we make one sample equal one cell transfer. We start the block transfer here, and then these 2,000 samples get played out in hardware with no software running to keep it going for the next 2,000 samples. You almost never start a cell transfer in software, because if you're doing that, you may as well just use an interrupt service routine. You are going to, for this lab, and if you are writing software in general that transfers data using DMA, you're going to specify a block transfer, so a whole ton of data gets moved by hardware. But wait, there's more. You've got your basic transfer mode, which is what I've been talking about, which is memory to memory. But remember the special function registers, that's code word for I/O, like timer registers and other memory locations are memory mapped so that any peripheral can be read from or written to. There's a pattern match mode, which means that you can write, you start a block transfer in software, and the block transfer continues until the hardware notices a byte match, a bit match in a byte, and then the transfer stops, it aborts. This is very nice for sending serial data because strings always end with a null. That's how C terminates a string. So that if you start a transfer to the UART as a block transfer of a string, the whole string will be sent with no more software interaction. The UART goes off and sends the data, and when it's done, or when the string is ended, the DMA sends a null. The DMA controller notices the null and aborts the transfer. So pattern matches is a conditional. Oh dear, you can do conditional execution. Does that mean you can do general computation with the DMA unit? The answer is yes. Channel chaining mode. The end of one DMA channel can trigger another. I haven't found how to use for that yet, but I'm sure there is one. Channel auto enable means that you have hardware auto looping. Oh, it's like a while one loop that loops over memory addresses with no software control. So once you start this guy running, it runs forever until you abort it. Why would you do that? Well, let's say that you want to generate a periodic signal like a sine wave indefinitely. You build a table with the sine wave values. You start it with a block transfer. If the block transfer is on auto enable, you get to the end of the sine wave buffer, it starts again and just keeps going and just playing the sine wave cycle over and over again. In other words, you get a never-ending periodic signal. We've actually used that in a scientific instrument because with DMA output, you can get over 3 million analog samples a second out through a DAC for making really high quality audio rate signals for doing impedance analysis. And last but certainly not least, there's the special function module, which does a bewildering bunch of different things. It does bit and byte reordering. So if you need to change big endian to little endian, you can do that in hardware with a DMA channel. It can also access a linear feedback shift register implementation of a cyclic redundancy check generator. Therefore, you can do error checking in the CRC sense by passing a data stream through the DMA channel, and at hardware rates with no CPU interaction, you can generate a CRC code for data transmission or decode CRC for data reception. As a side effect, you can also generate high-speed random numbers and a few other things. And these are not mutually exclusive functions. You can do all these at the same time. It's highly programmable. It's a complicated chunk of hardware. It's as complicated as a CPU, but programmed differently. We're going to use it for a few simple things, but like all of the peripherals on this chip and like on any microcontroller, what you have is a toolbox for building cool stuff. There's no limit on the number of ways you can concatenate these hardware objects to do interesting computation. So in the last minute or so, any questions at this point about DMA? I'm going to talk much more about it. Give you a couple of examples. But you might want to look at the DMA page, which has a couple of examples on it. One pretty simple example. A waveform generator using DMA, and then it turns out that ProtoThreads uses DMA, optionally uses direct memory access to send strings to the terminal, and that's a little more involved because there's a bunch of error checking that needs to be done. And if you're still more interested in that, I'll give you a reference to the stuff that Tamid did. Any questions? See you in lab.